It does. It'll go back and forth, and you can set it to below as well. Okay, so last time we left off on the second part of the competitive inhibitors. So again, the competitive inhibitors are going to increase the apparent value of Km, because keep in mind that we now have something that will bind to the enzyme independent of the substrate, right? Another way of thinking of that is it's going to be like you added something that pulls out one part of that equilibrium. So if you kind of remember your equilibriums, right? Okay, we have an equilibrium right here, right? So what happens if we pull this enzyme out of this equilibrium? The equilibrium starts favoring this side, doesn't it? Okay, which means that we have increased our Km. We have made it so the Km looks like it's larger. Okay? Everybody see that okay? All right. Okay, so the new apparent value of Km is going to be approximately this right here. The new Km, as it were, equals the Km times 1 plus the inhibitor concentration divided by how well that binds, which is the Ki, right? The inhibitor dissociation constant like thing. The Km for the inhibitor, as it were. Okay, and everybody understands how to read that, and nobody has any issues, right? Fantastic. Okay, so remember that with the inhibitor, if it's a competitive inhibitor, what does not change? Your Vmax, right? Your Vmax is not going to change. Because if we put enough substrate, we can still get the Vmax, can't we? Yeah, we can outcompete our inhibitor. Okay? I'm trying to get you to logically get there rather than try to memorize every single one of these and then forget them and not have it later. So our equation that describes our Lineweaver-Burke plot would actually look like this for a competitive inhibitor. We just substituted in that equation part that we got before. And what you'll notice here is that we've essentially changed our values that would have went with our Km values, right? Our Vmax's basically stay the same. Okay? And again, we've kind of rearranged this. This would be our x right here, y. This would have been the y-intercept, right? So don't get tricked by the y-intercept moving. Okay, so this right here would be no inhibitor being present. That would be our Lineweaver-Burke plot. And if you remember correctly, this value here was negative 1 over Km. This right here, which is the y-intercept, was the 1 over Vmax, right? And then the slope was Km over Vmax. Everybody okay? Okay, so if we add a competitor inhibitor, what's going to happen? Our Km values will change, right? So everywhere our Km would show up, those are going to change to become a larger Km value, right? Okay, so 1 over Km here, that will be a smaller value closer to 0, won't it? Okay. The slope was normally Km over Vmax. If we increase the Km, the apparent Km, then we're going to end up with what? Steeper slope, exactly. You got it. Right?
Well,
you're getting it.
1 over Vmax, and that's the y-intercept.
It is.
Over Vmax is the slope. What was
Exactly.
the first one you said?
The negative 1 over Km, that's the x-intercept. That's down here. Okay. Okay, fantastic. Okay, so now keep in mind, so we're going to have on-competitive inhibition now, the on-competitive inhibitor working on this now. So remember that the on-competitive inhibitor can only bind the enzyme-substrate complex, and thus the on-competitive inhibitor is always going to make an ESI complex, right? A complex with both of those attached to the enzyme. So because some of the on-productive ESI will always be present, this is going to be where we lower our Vmax. We can't outcompete it, can we? Because if we bind the substrate to it, then we just make it easier for the damn inhibitor to bind. So we can't actually get rid of it of its effects, excuse me, by increasing the substrate concentration. Do you see that okay? Okay. We're not competing with it, are we? In fact, having more ES just means the inhibitor will have more expression of its inhibition, right? Okay. So the uncompetitive inhibitors are going to lower your apparent value of Km. This is because the inhibitor is going to bind to the AS. Again, you can think of this as the same equilibrium functions we talked about before, right? So what happens if we lower the ES concentration? Is it going to go backwards to E and separate S as much? No, because it can't separate now, can it? Yeah. So we've went ahead and shifted this equilibrium towards the enzyme substrate binding together, don't we? Okay? And staying together. All right. Note, however, we can no longer go to product, so our Vmax lowers, our Km lowers, we've lowered both. Okay? Or I should say the Km value, the apparent Km value will actually be a larger value. Sorry if I confused anyone.
So the Vmax lowers.
Yes, the Vmax lowers. The Km is going to, yes, increase. Now, this does do an interesting relationship with the line mover Burke plot that you may not have thought when I said these things, okay? And that's that the changes in those two values are proportional. If we change both values on the top and bottom of a slope by essentially the same amount, what happens? We don't change the slope, do we? Yeah. Yeah. It's something that you don't usually connect until you see it, okay? And so what's going to end up happening is, again, our slope is our Km over Vmax, right? And so this is the no inhibition, this is the uncompetitive inhibitor right here. And so what we're going to see is our slope doesn't change, it stays the same, okay? And this makes it very easy to spot when you're looking at line mover Burke plots. Because if your slope doesn't change, uncompetitive, right? But what does happen is our y-intercept and x-intercept both change. Okay? The x-intercept is the negative 1 over Km, right? The y-intercept is the 1 over Vmax. Okay? This is how you would actually incorporate the inhibitor relationship into this, in case you're curious. Okay, now one last question. How do I tell which direction my Km goes? Does it get bigger or smaller? So what I look here is this value right here. Okay? That's negative 1 over Km, right? So if it moved this direction, that means that Km had to have gotten smaller, right? Yeah. I don't remember which way I said when I was... Did I? Okay. So correct that. It got smaller in value. Okay? Or another way of saying that is the binding was increased. Yeah. I do have an issue where I sometimes say increased. I mean binding increases. And yeah. Because I'm used to talking about this in binding, right? I'm talking binding here. But Km is the dissociation. So this one's going to be the non-competitive inhibitor. Did you all understand this okay, the uncompetitive inhibitor? Okay. Okay. All right, so the inhibitor is going to lower the concentration of your functional enzyme in the case of the non-competitive inhibitor. Essentially, we end up sticking your enzyme, you basically get inactive forms that still bind, right? And so you just stop its ability to do its normal function of going to product. So again, that's going to functionally lower your concentration of your functional enzyme. The apparent value of Vmax is going to be decreased. This will be decreased to this apparent value of Vmax, which incorporates this binding of the inhibitor. See that? Okay, so the Km, however, is going to be unchanged because it still binds, doesn't it? We haven't changed the binding at all. All we did was change the amount of product we can make. Okay? So it still binds to the enzyme inhibitor complex, or if you don't have the inhibitor, it still binds to that. Doesn't change that at all. But what it does do is it changes the amount of product we can make from those. Or another way of saying that is it essentially just lowers the enzyme amount, period, right? If we lower the enzyme amount outright, what happens to our Vmax? Goes down. Yeah, it goes down. So the non-competitive inhibitors cannot be overcome by increasing your substrate concentration because it doesn't matter if we bind the substrate or not. The inhibitor just stops it from making product. Okay? And the other way you can look at this is that it affects both sides of the equilibrium the exact same. Okay? So it can go backwards or forwards, but you just bind the inhibitor on there and it can't go to product. That's it. So if you have an EI or an ESI, they basically end up being the no product either way. But it doesn't change the binding of the substrate. It can go back and forth between ESI and EI. Okay? God, sounds like I'm saying EI. Okay. Again, we've lowered the apparent amount, and so Vmax is going to go down. Km, however, will not be changed. And that's what we see right here. Remember, the x-intercept is actually the one that corresponds to negative 1 over Km, right? And so our x-intercept will stay the same. We'll get a change in slope and a change in the y-intercept on the Lineweaver plot. Now, again, remember, this is 1 over the Vmax here. And so we're actually going to get higher up on this y-axis, okay? And if we remember our equation, the Vmax here was the bottom. If we lower the denominator, we're going to get a larger slope, right? Okay. Okay, so the transition state analogs, these are going to be potent competitive inhibitors of enzymes. Literally, you're making an analog for the transition state that's going to stick there and get stuck, right? So again, the analogs for transition states are going to be compounds resembling the transition state of a catalyzed reaction. Right here we see a catalyzed reaction. Here we have a planar transition state. So what we've done here is we've made this, see we put double bonds in it, and so it is forced to be planar, isn't it? And now being forced to be planar, when it gets in there and binds, the enzyme's going to bind it as if it's the transition state, but it can never go to product or reactant, can it? Because it has those double bonds. Okay? Irreversible inhibitors, these are going to be inhibitors that covalently bind to the enzymes. These can be powerful tools for elucidating the mechanisms of an enzyme activation because you can bind specific side chains and see which one knocks out activity, right? And any of them that knock out or change activity, those are involved in that mechanism, aren't they? Okay. So some of the major types of irreversible inhibitors, these are going to be group-specific reagents. You know, we have a lot of nitrogens on there, right? There's like a whole list of reactions I gave you that worked on nitrogen and sulfurs, wasn't it? Yeah. So what do you think are good targets for that? I know, right? All right. Affinity labels. These could be reactive substrate analogs. Basically, they're substrates that would attach, and then they're more reactive than they should be, so they'll bind and make covalent bonds at a decent rate. Okay. These don't have to be super reactive because they're going to react in the right spot, having binded as a substrate, right? There's going to be mechanism-based, which are suicide inhibitors. Okay, so this right here is a group-specific reagent. This is going to inhibit the enzymes by reacting with specific side chains of your enzyme's amino acids. In this case, we have serine, the OH here. And so this is DIPF. What we see here is it comes in, it's going to react with the alcohol, and it will then fill that site. See that? And so this will actually completely block that active site. This is actually an affinity label. These are going to inhibit enzymes by being structurally similar to the substrate and covalently bonding to the active site residues. So what we have here is the natural substrate for the chymotrypsin. This is the chymotrypsin, by the way. This right here is then the specificity group. That's the group that's going to target the normal binding of the natural substrate for chymotrypsin. So it would have that same sort of interaction and bind there, right? And then what we would see is that this then has a reactive group over here that's going to react in that binding site. And so it'll get stuck there with a covalent bond. Okay? Finally, we have the mechanism-based suicide inhibitors. These are going to bind to the enzyme as a substrate. The mechanism of the catalysis that normally generates a chemical reactive intermediate with the enzyme is going to end up inactivating the enzyme through covalent modification. So it will go along with the normal reaction that should catalyze. But that reactive intermediate then reacts with the site. Okay? All right, and so this right here is actually an antibiotic, penicillin. This is a natural antibiotic, by the way. So this was actually designed by nature, right? So just to let you know, these things, these covalent modifications to your enzymes, these do happen actually. You do this to yourself all of the time, okay? And purposefully so. And we'll talk about that more when we talk about enzyme regulation inside your body. But this is, again, a suicide inhibitor. So it's going to inhibit the formation of your cell walls in certain bacteria. This right here being what it looks like. And this is the bond, the groups here that would normally attach. This right here is your highly reactive bond that's going to break and then cause that covalent modification. So this is actually the schematic representation of the peptidoglycan in Staphylococcus aureus. This is the peptidoglycan right here. This is a linear polysaccharide chain cross-linked by short peptides. And you can actually see the chains cross-linked by the short peptides here. This is actually part of the cell wall. This right here is the different groups and how they're related to each other. So the transpeptidase, this is a glycopeptide that's going to catalyze formation of your peptide crosslinks. Again, it's making these crosslinks, right? So that the cell wall has integrity. Without the crosslinks, they'd be fibers that would just split apart, right? And so you won't make a cell wall and you won't stay together. Or at least you'll break very easily. And so what we're going to see here is the transpeptidase will react, will proceed through an acyl enzyme intermediate. And this right here is then the beta-lactame ring. When it tries to go for this group and it does its normal catalytic activity, what's going to happen is this reactive bond is then going to open and it will react with the site, sticking in there, deactivating the enzyme, right? Okay, and this is actually where you're seeing it right here. This is the enzyme active site. We have penicillin come in here. It binds, it ring opens, and covalently modifies that reactive site at that serine, right? Okay. Everybody see it okay? Okay. And this at this point will be an inactive enzyme. We've knocked out any future ability to make this with that enzyme. We would have to make a whole new enzyme to keep doing this, right? Yeah. Which, by the way, is why you can have a minimum amount of penicillin you need, because you need to actually knock out all the enzymes, right? If you don't knock out the enzymes, it could still go forward, okay? And it can make new enzymes, so you actually have to keep at it. Okay. Stop